When we studied stellar evolution, we studied the process by which stars are formed out of gas and dust that exists in the interstellar medium, and how these stars form their own system consisting of planets, satellites, dwarf planets, and asteroids and comets and gas, and how eventually these stars uh, finalize their life term, and in that process they undergo what we call stellar death. So this process takes, in the case of stars like our sun, about 10 billion years. Stars that are less massive, they take much longer, and stars that are not as massive, or much, in fact, much more massive than the sun, they take this process in a very short amount of time if we consider the astronomical time. So this week we are focusing on the evolution of low massive stars. First of all, don't forget that what drives evolution of stars is the mass content of stars. So stars that are less massive than the sun, as I mentioned before, it goes very, in fact, the stars much more massive than the sun, they go very, in a very short amount of time through their evolutionary stages. And stars that are much less massive than the sun, they take much longer. And the reason for that is energy production in the star depends on pressure in the core where these fusion reactions are taking place. And low mass stars, the pressure at the core is less than it is in a high mass star, and the temperature in there is less than it is in a high mass star, and as a result the time in which this fusion reaction takes place is much different. Uh, and I'm keeping talking about low mass star, high mass star. What are the difference between those? Low mass stars technically are stars with mass content less than 8 solar masses, and more massive than that, the star will take a route, evolutionary route, that is slightly different. So stars that are less than 8 solar mass, they end their lifetime as a white dwarfs. And stars that are more massive than 8 solar mass, they end up their lifetime as neutron stars or black hole. Neutron stars or black holes. Okay. So in this slide, you have a slide showing an HR diagram, Hess-Brown-Russell diagram, and yes, um, we should learn this material because it's a core material in our course. These lines indicate the progression of stars as they formed out of the material available in the interstellar medium. Let's take this track here, this evolutionary track that ends up as a star like the sun. So a star like the sun starts its evolutionary life as a young member that is, as you can see in this graphic, it can be up to 1,000 times more energetic than the sun itself. So the sun is listed as one unity of luminosity, right? And remember, luminosity is energy. It's the energy the star itself is putting out in the space. But a star like our sun can be observed, can be probed by telescopes, and astronomers using spectroscopy or photometry, they can infer stellar properties as we studied in chapter 10, and find out that altogether this young star is putting out as much energy as, look at the graphic, 100 times or 1,000 times more than the sun itself. Just for comparison, if the sun is a 100 watts light bulb, a sun as a young star produces as much energy as 1,000 times that. Does that make sense? And then what happened after that is the sun slowly contracts, because as the sun is formed, as you can see in the graphic, its surface temperature is less than it is right now. The sun right now is about 6,000 Kelvin. The sun as a young member appears with surface temperature slightly bigger than 3,000 Kelvin. So therefore cooler, therefore redder. That's one of the things we learn in this course, that cooler star tends to be redder, and hotter stars bluer, right? Or go to the whitish range. So the sun appears as a cool star, as very luminous, which means big, it's a big star, and it slowly contracts. And as it contracts, the amount of energy sent out to space diminishes, because the whole surface area that is producing radiation, that is emitting radiation, diminishes. And eventually the sun is contracted to a star slightly bigger than it is now, but with a core temperature and pressure capable of igniting fusion reactions. And that's why the sun becomes what we call a mature star. So as you can see in this HR diagram, this is true for all other stars, right? All with exception of those that are very massive, their evolutionary track is such that the change in luminosity between formation stage and main sequence stage is not that great, but it is for low massive star. Okay. So this sequence, these tracks are called pre-main sequence tracks. So are the evolutionary steps of stars prior to entering the main sequence. Now this diagram here shows one interesting aspect of a young star, and that is, if you could take a scoop of material in the stellar surface and the stellar kind of a middle part and the core, the scoop would show a chemical abundance that reflects the chemical abundance of the interstellar medium, which is most of the gas content is hydrogen, 75%, and the remaining gas content is helium, with trace amounts of everything else, right? And we saw that before. But as the star evolves, or as fusion reactions takes place in the core, as hydrogen in the core, 4 atoms of it gets fused into 1 atom of helium. As this takes place, look what happened. The concentration of helium in the core rises to the point that when the stellar evolution is completed and the core is a helium core and no longer hosts hydrogen fusion reactions, something different happened. The star has to undergo changes. So the first stage in stellar evolution is called the pre-main sequence stage, in which the star contracts to achieve the stage we call main sequence, when the core is going to be dense and hot enough to host fusion reactions, and these furnaces is producing constantly helium atoms, since atoms of hydrogen are fused, creating helium atoms. And energy is a byproduct of that. So that energy is the one used to keep the sun stable for a long time. Okay. But see what happened. So hydrogen is being used up, used up, used up. So eventually the hydrogen is gone in the core. There is no convection taking material or circulating material between core and shell. It doesn't happen. So the core hydrogen is over, it's over. Now we have a core of helium, so what happened? When helium core is formed at a temperature of about 20 million kelvins, and with the pressure there is, those conditions don't match those necessary for helium fusion reactions. So helium cannot fuse into heavy atoms, and those heavy atoms are carbon and oxygen. So helium cannot fuse at 20 million Kelvin with the pressure that low mass stars will produce at the core. So what happens? Well, what happens with any gas, normal gas? The pressure of the outer layer, the weight of the star on the core, will force the star into some contraction. The core contracts, and this is what's being shown here. The core contracts. Wait a second. Not here. Here. The core contracts and heats up. So now you have the core diminishing its volume, going from, and you know, in nature, when you confine gas and you contract and you reduce the volume, the gas temperature rises because you're forcing the elements, the constituents, to collide more vigorously, and as a result temperature grows. The kinetic, as we say, the kinetic energy of the gas goes up. So as the volume in which the core lies, as the volume contracts, the elements in there will collide more vigorously among them, and the core temperature rises. The pressure rises as well because the volume is being reduced. So what happened in the outer core? Well, in the outer core something interesting happened. The shell surrounding the core, the shell surrounding the central core, right here where I'm showing, this shell is now undergoing what astronomers call shell fusion reaction. Hydrogen in the shell is being converted into helium and energy is being produced. This energy migrates and flows outward and is responsible for bringing an imbalance between gravity and this outward radiative pressure. As a result, the star expands because now gravity cannot overcome the pressure that is the result of energy produced right here in this figure in the core. So the star expands, and this expansive phase is called red giant. And why red? Well, it's red because now the atmosphere is growing in volume, and the elements that are part of the atmosphere, they collide less because the atmosphere expands, there is less collision going on, and the temperature falls down. So see, two things happen in kind of the opposite way. The core contracts and heats up. The outer shell expands and cools down. The star is called a red giant. Okay. Now, the red giant is the next stage in the Posman sequence evolution. There you go. So what happened? Well, now you have a hydrogen burning in the main sequence. Now we have a hydrogen burning shell surrounding a dormant core, and eventually this dormant core is awakened when temperature reaches 100 million Kelvin level. At that level, fusion reactions can be ignited again in a core, but not hydrogen fusion reactions, but helium fusion reactions. And the star is called the asymptotic giant. And the star is called the horizontal branch star, in which you have a stable helium burning core. So the helium atoms are being burned and fused into carbon and oxygen. There is a surrounding shell of hydrogen burning material that releases energy to the star. And as it happened before, eventually this phase called horizontal branch phase ends because the core is a compact core of carbon and oxygen atoms. Helium is gone, fusion reaction cannot take place, and carbon cannot be fused at 300 million kelvins. It's not that hot, and the pressure is not enough to ignite that fusion reaction. And that leads to the last evolutionary stage in a Posman sequence phase, when the core contracts again, a carbon-oxygen core contracts again, heats up, a hydrogen and a helium burning shell are formed outside the core, producing fantastic energy that expands the star into what we call asymptotic giant branch star. Asymptotic giant branch star. And as AGB, asymptotic giant branch star, as an AGB, the star luminosity outshines whatever happened before in the life of the star. Is something as luminous as 10,000 times the solar luminosity. So imagine the sun is born as 100 times, or probably 10 times. Let's go back to, let me show you what I'm trying to say. Right here. A star like the sun is born with 100 times, about 100 times or 1,000 times solar luminosity. So if you take the sun as it is now, as 100 watts light bulb, as a newborn star, it is born as 100 times or 1,000 times as luminous as 100 watts light bulb. And the reason for that is because this young star is too big. Okay? Now, as a red giant star, it reaches a position which is again kind of 100 times, 1,000 times as luminous as the existing sun right now. And when it becomes an AGB, it becomes as luminous as about 10,000 times as luminous as the sun. Okay. Now, the core keeps releasing energy in flashes, and this outer material surrounding the core is eventually expelled into the interstellar medium, and we call these systems planetary nebula, consisting of a central white dwarf surrounded by an expanding shell. So planetary nebula is a white dwarf in an expanding shell. This expanding shell, and they are gorgeous. If you look at pictures, look at this. Aren't they gorgeous? So planetary nebula, they really have gorgeous pictures. So imagine all this gas being once concentrated in what we call a star. And now the core of the star we call white dwarf. You see all these stars, all this nebula has a bright central core in it. So all this central core is a white dwarf. It's a hot compact material, Earth size, the size of our planet Earth, 50,000 or more Kelvin temperature, made of degenerated material, carbon degenerated. Some of these white dwarfs, if they happen to be members of a binary system, they might trigger matter from the companion onto them. And and as this material falls, it might also be ignited in a short amount of time, brightening in what we call nova. So nova is white dwarfs with material that is being dumped on it by companion stars that light up in a very short amount of time, and the luminosity of a nova can be sometimes 100,000 times to 1,000,000 times more luminous than the sun, because it's a flash. It comes in a flash, and that luminosity fades down in a time scale of a few days. Now, a white dwarf was calculated to be some object that cannot be more massive than 1.4 solar mass, or explodes as a supernova. The material becomes stable. So if the white dwarf is member of a binary system and the companion dumps material to the point of transpassing this limit of 1.4 solar mass, the entire star explodes because it becomes unstable. And that explosion is equivalent to a energy release of 1.4 solar mass. So if you take 1.4 solar mass multiplied by c squared, c is the speed of light, you have that converted into an energy that is released. This is called supernova type 1a and is used by astronomers to map out the galaxy, to map out the universe. And those are the main issues surrounding this chapter on evolution of low mass star. I recommend you googling NNAP astronomy lab modules. Right here, and then go to interactives, and then I recommend that you do this exercise on stellar evolution, exercise number 1, 2, 3, and 4. It really helps you to understand better what it means exactly, stars being in the HR diagram, stars migrate in the HR diagram. They really don't migrate, they don't move, but the ratio between their stellar energy output and surface temperature change as they evolve. Okay, all right, thanks for listening.